At AAON, we aren't afraid of taking risks or doing what no one else is doing. We are a group of great people doing great things. Innovation, empowerment, sustainability, partnerships, perseverance. This is all part of our DNA. Since 1988, we have been pioneering a new way in HVAC solutions, and we want to share our stories with you. Expect a diverse range of episodes, from technical deep dives to uplifting stories, along with insightful discussions about the HVAC industry landscape as we see it at AAON. This is a deeper look inside AAON.
Welcome to episode 5 of Inside AAON, where we're going to be talking about heat pumps, which happens to be the segment of our industry that is growing the fastest at this time. Today, I have, as always, my partner in crime, Whitney Tapp. Whitney, say hi.
Hi.
And we have two guests today in our episode. The first one is a returning guest, Kevin Teakell, or the Kevin Teakell. So welcome. Thank you for being here with us.
Thanks for having me again.
Absolutely. And then we have Josh Walker, our Senior Manager of Product Engineer. Your first time here, so welcome to Inside AAON. And we can now say you are a cool guy at AAON. Thank you so much for your time.
Thank you.
So to get started, how about if you tell us a little bit about what you do at AAON, what your role looks like?
Okay. So recently I was promoted to Senior Manager of Product Engineering.
Congratulations.
Thank you.
Yeah.
And so Product Engineering, that team kind of acts as the central hub of information and documentation for basically all of our products. So they're kind of like the central location where, we work with, a variety of different teams, from sales to aftermarket to the R&D team to help develop products. So I lead that team.
That's excellent. Well, congratulations on your promotion.
Thank you.
We're in good hands, I think. Okay, so to start on the topic of heat pumps, could you tell us a little bit about what are heat pumps and how do the heat pump work?
Yeah, because it's not always entirely clear, how you can produce this 90-degree entering room temperature from a really cold, chilled source.
Okay. So a heat pump kind of acts the same as a normal air conditioner like you would have at your house, right? So, at your house, you would have an indoor coil who, essentially takes heat from a lower ambient air and moves it to the outside, which is normally a higher temperature, right? So in a heat pump, you add a reversing valve, you change the cycle, and during heating mode, you would take, heat from the ambient and add it to the indoor coil. Essentially, it's the exact same cycle as your normal cooling unit.
And to terminology, ambient, we're referring to the outside air. Correct. Perfect. Awesome. I appreciate that. Kevin, one for you. In recent times, heat pumps have become the solution to a problem that we are presented to as a society, and that is pollution, contamination, efficiency. And heat pump had become not only popular in the areas that they have always been utilized, but now they're being utilized in areas that they were not as commonly seen. Could you tell us a little bit about how heat pumps help efficiency and decreasing that pollution?
Okay, sure. So let's take a moment, though, and talk about efficiency, okay? It's kind of a misnomer out there that heat pump efficiency is, people talk about efficiency in heat pumps. So let's kind of take it back to the very fundamentals of heat transfer. So if you look at, for instance, the first law of thermodynamics, I'm not going to get real deep on this, but when we talk about a gas furnace, okay, a gas furnace is where we take gas, natural gas, propane, something like that. We ignite it and we burn it to make heat, okay? So in that process, we're doing an energy conversion from a gas to heat. Now, in a heat pump process, we're actually doing an energy transfer. We're transferring from the outside to the inside, or from the inside to the outside, depending on whether we're heating or cooling. So that's a different process. Now, when people think about efficiency, and again, use that term loosely when we're talking about heat pumps. When they think about that, they're thinking about we may have a COP of 3, okay? COP is the coefficient of performance. So that's the amount of heat, if we're talking about heating, it's the amount of heat you get out versus the amount of electricity you put in. Okay, so it's the heat watts versus the electricity watts coming into it. So a lot of times you'll see on a heat pump, we may have a COP of 3 or maybe 4, okay? And some people will think, well, that's like an efficiency of 300%, okay? Well, you can't have, by the first law of thermodynamics, you can't have a 300% efficiency, okay? So and that kind of comes from, traditionally we either heated with a gas furnace, okay, or we heated with electric heat strips. Well, electric heat strips have a 1-to-1 ratio, a coefficient of performance of 1, because you put in 1 watt of electricity and you get 1 watt of heat out of it, okay? Whereas that heat pump, you're getting maybe 3 times, 4 times that of electricity, of electric heat. So, some people will take that, or actually a lot of people, it's very common to say this, that, my gas furnace is 85% efficient, but I have a COP of 3, so it means I'm over 300 times more efficient than I would be with a gas furnace. And that's not really correct, because those are different processes. The gas furnace is an energy conversion process. A heat pump is an energy transfer process, okay?
So transfer is not conversion.
That's not conversion, okay? But again, it's very common for people to say that. So, as we talk about, the evolving world around us, and, there's a lot of companies and states and governments around the world that are saying we need to electrify everything, okay? So if you were to just go directly to electric strip heats, we would need a tremendous amount of electricity made compared to what we have today. So the way you can get more heat capacity is to go to a heat pump, because you get, 3 to 4 times more a capacity for the amount of electricity you put into it versus an electric heat strip. Okay, so those are kind of the differences there. But as we look to electrify more, that's really the way you would go. You go to a heat pump to do that, because electric strip would be very costly for one, but it'd take a tremendous amount of electricity generation as well.
So would you say, in a shorter version, why are air source heat pumps more efficient? Because I understand that your explanation is why the efficiency metric might not be ideal for comparison reasons, but they're still more efficient than your regular.
Efficient, effective, kind of however you want to say it. But yeah, it like I said, for every watt you put into it, you're getting 3 or 4 times the amount of heat capacity out of it. So that's why heat pumps are so great compared to just electric heat. So, to really electrify everything, that's what we're going to have to go to is all heat pumps to do that.
So kind of like speaking on commercial applications, when would like a building owner decide to use an air source heat pump versus like a traditional package rooftop or a chiller and a boiler system?
So, multiple reasons. Of course, you could have government mandates.
Yeah.
There's various places are saying we're going to be all electric by 2030 or 2035,
no natural
whatever.
gas.
No natural gas, right? Various companies have made similar kind of commitments. So, if you're a place that's made that kind of commitment, that's what you're gonna be going to heat pumps. But there's also a lot of places that traditionally went with heat pumps because of natural gas infrastructure. There's places that don't. A lot of places in the country where natural gas is not readily available.
That's readily available. Like
And
say Texas, Oklahoma.
Yeah, Oklahoma, Texas, we've got lots of natural gas, but you go to other places and they don't have that. So they're either using propane or fuel oil or some other things that are much more expensive to operate.
Yeah.
And so those are kind of some of the different reasons people would choose to go to a heat pump is, if you want an all electric solution, that's how you're going to go, because electric heat is just going to cost you a lot more. It may be a little less expensive up front, but over the life of the equipment, electric heat is going to be very expensive to operate.
So do these systems work for new construction or retrofit or both?
Yeah, it works in all applications, but if you're going new applications, new buildings, it's much easier because you're sizing, when you're sizing that building, you're sizing all your electrical loads for these new heat pumps that you have, and you can design the building around that. You can get your electric service set up for that. If you're doing a retrofit application, there's some things you got to worry about a little bit. When you go to an all-electric unit, so it's an electric heat pump, of course, but heat pumps don't work in all situations. When it gets too cold, you're going to have to go to some sort of backup heat, okay? Or at colder temperatures, a lot of heat pumps won't produce enough capacity, and you may need some auxiliary heat to supplement the heat pump. So when that happens, you're going to be, if you're saying it's an all-electric unit, then you're going to engage electric heat strips. Okay, and those electric heat strips are going to use a lot more power for that amount of heat capacity we get out, like we mentioned a moment ago, than you're going to get out of that heat pump. So now we're going to have this, the heat pump running and then maybe electric heat strips as well. We're going to need a lot more amps than what we're used to with just a regular air conditioner with a gas furnace. Okay, so when you do a retrofit application, you're going to have to look at, and we say it's an all-electric unit, you're going to have to look at the amps I need in all modes. So that's when the heat pump's running, when the heat pump's maybe running with some supplemental or auxiliary heat, and then also when we're running in full backup mode where the only thing running is the electric heat strips. So you're going to need to look at how many amps I need in all those different modes to figure out the worst case, and then that's what you're going to size your electrical panel off of. So in that retrofit, if I'm going in and I'm going to replace the units with all electric, a lot of times I'm going to need a bigger electric service going to that unit. Depending on conditions, it could be even double the amps that you had on your original air conditioner. So you're going to need a new electric service from your main building panel to your unit. If you've got enough units on your building that it's a big enough load, I may now need a new electric service to my building as well. So a lot of things go into a retrofit building. That's why we kind of, in retrofit applications especially, we kind of like the idea of what's kind of termed a dual fuel unit, where I've got a heat pump, okay, and then rather than using an electric heat strip for my auxiliary or backup heat, maybe we use a gas furnace, okay. So you're thinking, well, gas, I don't really want to use gas for whatever reason anymore, but when we look at using a heat pump, okay, that heat pump's going to take up almost all of the hours that you would ever need to run to get your heating capacity. There's a very small percentage of the hours of the year where you would need that furnace to run. But at the same time, if I do need that furnace to run, I could use the existing gas infrastructure I already have. I don't need to upgrade my electric service for my building or my units and all those kinds of things. And those small percentage of hours where I need that extra capacity, where I've got a really cold weather event or something, maybe I have a problem in the building or who knows what, I've got that opportunity to use that gas, like, again, a very small percentage of those hours, but it can really help, in those upgrade costs, and it can also help you make some decisions, right? If today my electricity is cheaper to run, maybe I run on heat pump, but tomorrow if I get a lot of my electricity from wind and solar, and maybe the sun's not shining, the wind's not blowing, and the electricity gets really expensive, then I could switch to natural gas. Okay, so it gives those customers some options. It's flexibility, it's options, and if you want to make decisions based on carbon, you can run the heat pump more. So there's a lot of flexibility and freedom using that dual fuel unit versus maybe going all electric.
Yeah. So to me, it's a little fascinating how we have seen in recent years heat pumps becoming very popular in areas where it was like not even a question whether you would use heat pumps. So from a product perspective, what happened that we are now using heat pumps in much colder areas that in the past we did not?
So a lot of that's been some of the technology that we developed around Alpha Class that allows us to run down to 0 degrees. We use variable speed compressors, variable speed condenser fans, and all those technologies allow us to have more of an omni-climate type approach to heat pumps than what we previously did. And then you combine that with gas heat backup, it makes for a very robust unit.
And this is a little bit with internal knowledge. A lot of our heat pump cells, Alpha Class, they're in areas that are warm weather. Why is that? Why are people in warm weather consuming a product that was technically designed for cold climate?
So multiple things can happen there. So, for instance, like Florida. Florida has traditionally been a very big heat pump market, okay? That's because, in Florida, it's all electric. They don't really have you don't have a lot of natural gas infrastructure, and they don't have a lot of cold temperatures either, okay? So there's not a lot of times a year where they need it. Traditionally, maybe they went electric strip heat. Over time, that's, it can be expensive to run that. So some places like that, some warmer climates have traditionally maybe used heat pumps for their very limited amount of heat they need in a year, because traditionally heat pumps didn't work that well at cold temperatures. But, as Josh said, with the advent of, variable speed compressors, which have, one of the big things about variable speed compressors, they have a lot bigger operating envelopes, so they can operate across a wider range of temperatures. And that's allowed us to get our heat pumps to get more capacity at these colder temperatures and work at colder temperatures. So it's enabled to just to move up to higher latitudes in the United States where maybe you wouldn't traditionally see a heat pump.
Yeah. So going back to the omni-climate concept of the air source heat pump, so the idea is to get to negative, for it to work efficiently at negative 0 degree or 0 degree. How does it work when it's not 0 degree? Do we get more efficiency? Is this product attractive for other type of weather as well, and why?
Yeah, absolutely. So, traditional heat pumps in the past, like were an excellent application for warmer weather type areas like Florida and Texas, because, for the most part, it just operated really well. When you add the variable speed, you can gain more capacity. And so essentially your COP and your capacity, the higher the ambient you go, the better it operates. So you can use these variable speed heat pumps, what we're calling the 0 degree Alpha Class, in a whole variety of climate regions.
Yeah, and even in Texas, right, where it's warm and hardly ever gets cold. Remember just a few years ago, right? They had the big freeze that lasted for a few weeks, right?
And shut everything down.
They were very cold temperatures.
Yeah.
So, when you get, even though maybe your ASHRAE design temperature says, I'm fine, I don't really need to go all the way to 0 or something. I'm sure just about everybody in the audience can think of days where we were much below our design temperature. Here in Tulsa, our design temperature is 13 degrees. But, just a couple of years ago, we were at minus 17, right?
Yeah.
So you would never design for that. But, you get those really extreme days. And when you have those extreme days, if you don't have the capacity to kind of meet that, or at least kind of operate, you could really freeze out a building, cause a lot of damage, right? If you freeze water lines and those kinds of things. So it's really important that you can operate in all these various climates, right? That's, again, why we say omni-climate. It's not just, these aren't just for cold climates. It's for all these different kinds of climates, even maybe warm ones where you think you may not need something like that.
Correct.
So when a customer chooses a heat pump, is there like certain features they should look for that's going to prolong the lifespan, or what is the typical lifespan of a unit like this?
It depends greatly on products. We like to say our products are the longest lasting out there. A lot of our products can last 20, 25 years or more, whereas probably most commercial type products that you see on the market are more about 15 years or so. And it depends where you are. If you're on a coastal region, they're not going to last as well unless you protect them really well with coatings and things like that. So it really kind of depends a lot. Heat pumps, some people will be concerned maybe about compressors, because with a heat pump, you're going to operate the compressor a lot longer, right? You're going to, more hours of the year, that compressor is going to be operating. There's kind of two trains of thought to that. You are operating more, but you're also, you don't have those long downtimes either where something could go wrong too, right? So, the life of heat pumps, we tend to see that they're kind of similar to what you're maybe used to with air conditioning. But again, it depends how you treat it. Okay, if you just put it on a roof and forget about it, maybe it won't last as well, right? If you never change the filters and you never clean your coils and those kinds of things, they're going to run a lot harder, and it's gonna impact the life. But
so the maintenance is kind of like similar to a package rooftop.
Maintenance is going to be very similar to just any kind of rooftop that you're used to. Yeah.
So let's talk a little bit about features, because you kind of mentioned a few features that are available when it comes to cold climate air source heat pumps already. And we have focused quite a bit on the efficiency part. But there is another reason why we're in business, and that has to do with comfort of the tenant, comfort when it comes to keeping computers and hardware safe at the specific climate. So what are some of the features that AAON offers with Alpha Class that customers, owners need to take into consideration for specifically about comfort for the people that they are doing this for?
Yeah, because nobody wants it to blow cold air when it's supposed to be blowing warm.
Exactly.
So some of the features that we offer with Alpha Class heat pump units is when you have our controls, we kind of do on-demand defrost cycles. So it's not on some arbitrary timer. It's based on the actual conditions of the unit. And so that kind of limits the amount of times that you're not getting the leaving air temperatures that's uncomfortable, right?
Yeah, with a heat pump, you've got, the outdoor coil is going to be running very cold temperatures.
Yeah.
Okay, so and of course when it's running cold, the outdoor coil is now our evaporator. Okay, so our evaporator is always going to, if there's moisture in the air, that it's going to condense on that coil and drain off. Well, when it's below freezing, it's going to start to freeze on that coil, and it starts to affect the heat transfer of that coil. So so often we've got to reverse the cycle, and then we're going to run it basically as an air conditioner kind of at that point. Okay, so we want to really minimize the amount of time we do that. So we kind of adapt to the conditions. So we'll look at the suction pressure of the system, and we'll adjust timing, and based on the last time it went through a defrost, how long that happened, we kind of adjust over time. So that's kind of the adaptive defrost part of that. So that kind of helps it run more efficiently, longer. We want to run the heat pump as much as we can, because when we switch to the defrost mode, we're going to be putting cold air into the building. And we can do things like, if you've got electric heat, we can bring that on to help temper that air, so we're not dumping as cold air in the space and things like that. So those are very important for a heat pump system to operate the best it can, to provide the best comfort we can. I'll add too, like we mentioned earlier, variable speed compressors, the ability for those to adjust to varying conditions. We also do two-step compressors and digital compressors in heat pumps. So we offer all these various things so that people can kind of pick the different options that suit their needs. Okay, if you want a simpler unit that's not as complicated as a variable speed unit, you can go with two-step units, two-step compressors. It can be very affordable to do that and still get great performance. It may not get as cold a temperatures as you could get with a variable speed, but depending on your application, you may not need that. Another important thing I think it's to talk about is the difference between a commercial building and a residential building. Okay, your home is very climate dependent. Okay, in your home, it's you've kind of got a small volume versus the outside skin of your home. Okay, the outside walls. So the colder it gets, the quicker it's going to react to those changing conditions versus a commercial building, right? A large commercial building, we've got a lot of volume and not as much outside skin. So it doesn't affect it as much. Also in commercial buildings, you tend to have a lot more people. You've got a lot, copiers and lighting and computers and all these extra heat sources. A lot of heat sources in a commercial building, right? So they tend to mute the amount of heat you actually need. Even here in Oklahoma, and I'll use AAON's office building for instance. In the core of the building, even in the really coldest parts of the winter, we're still doing air conditioning. We're still cooling. Now the perimeter of the building, we're probably got heat going on, but in a lot of commercial buildings, you don't really need a lot of heat. Okay, even in the coldest parts in the country. So commercial buildings tend to be a lot different than what you may, a lot of us tend to think, my house, when it gets cold outside, it gets cold in my house. So I got to have, a lot of capacity to deal with that, but not so much as in commercial buildings.
And to react faster than in a commercial building.
Yeah, commercial buildings, it's more delayed, takes longer. But again, it doesn't take near as much heat either, because we just have so many internal loads in our commercial buildings. And then as well, a lot of commercial buildings don't really operate that much at night. Most commercial buildings will do what's called night setback, where we'll turn back, we'll reduce the temperature in the wintertime. We'll maybe, instead of having it 72, we'll make the building 65 or something.
Which again might be opposite for the residential.
Right. In your home, you want to be warm, right? Whereas in a commercial building at night, don't need as much capacity. We're going to turn it down. So, and that's also in the wintertime when you tend to have the coldest temperatures, right, is in the middle of the night. So several reasons why you may not need as much heat in a commercial building as you do in your home.
Correct. When you were talking about the different features that we have, it reminded me to something that we have said in the podcast before, is we make products for our customers. We don't go and look for customer for our products, right?
Yeah, we in general, we want to make products that our customers want.
Yeah,
okay?
that feeds their
It's
needs.
really important to meet the need of our customer, regardless of where they live or where they're coming from. It's we want to let them decide how they want to operate their buildings.
So there's no doubt that air source heat pumps have a place in our industry, have a very important place, and they're becoming more and more popular. Question, why have not air source heat pump dominated the industry to this point?
Yeah, I would say it's a lot of the reasons we were talking about earlier, right? Historically, heat pumps didn't have a lot of capacity, especially at colder temperatures. And that's probably the real driver, was just that. And the simplicity of using a furnace, too. It's fairly easy to make a furnace and then use your fuel to burn and heat your buildings off of that. So as maybe the way we want to consume energy changes over time, it makes it a little more difficult. But, we're developing a lot of technologies to really solve these problems, to go to these much colder temperatures and get much more capacity. So there's a lot changing. So, there's been some changes that have happened residentially, and now it's kind of starting to happen in the commercial space as well.
Yeah. From the product perspective, it has to do about technology. Who do we partner with, and so on? What else has changed lately that is making air source heat pump more attractive to the customers?
So we've been working with our vendors, some of our compressor manufacturers, and there are new technologies that are coming out, and we're working very closely with them to help essentially spread this air source heat pump or Alpha Class technology throughout different climate regions.
I'm curious, you have mentioned earlier about the controllers. We have AAON controls in Kansas City, Missouri. What role and how important of a role do controllers play when it comes to air source heat pumps?
So it's a very important role. So our research and development team works very closely with the controls department to develop essentially state-of-the-art sequences that keep the unit operational throughout the different climate zones by doing compressor envelope control so that we can protect the compressor basically in any operating environment. And it just essentially makes the unit extremely reliable.
So this is a question I wanted to bring up. I keep hearing about this DOE challenge. I know they recently, was it last year where they did the residential version of it, but now they're doing a commercial?
Yeah, residential was a couple years ago. And then here just in the last few months, they put out this, essentially it's the cold climate heat pump challenge for commercial equipment. They're Better Buildings Heat Pump Accelerator, I think is kind of the main title.
And AAON is participating in this,
we
right?
are, so yeah, we signed on.
Do we win something for number one?
Respect.
When we're number one?
we will win the challenge, of course.
Yeah, okay.
So they put out this challenge, and they've got some different specs. There's going to be a couple of phases of what they expect, but they've given us the general specs for the first phase, and it sounds like there's still a bit of negotiating going on with various companies and DOE on this spec. But in general, we expect it to require us to have basically 90% capacity at 5 degrees. So there's a term known as kind of capacity ratio, okay, when you start talking about heat pumps. So at 47 degrees, it's kind of considered to be 100% capacity. Okay, and the capacity typically goes down as it gets colder outside. So, typical traditional heat pumps, probably at 5 degrees, if they even run there, would be at maybe 30% of the capacity you get at 47. Okay, so that's very low, which means at that temperature, I'm going to need a lot of supplemental heat, a lot of that either electric or gas supplemental heat to get me to the temperature I need to keep my building warm. So, our Alpha Class heat pumps with the variable speed get about 30 to 40, maybe 50% more capacity than that, which is great. But it's still maybe not enough at some of those really cold temperatures that you wouldn't need any supplemental or backup heat. So the heat pump challenge is going to require at 5 degrees that we have 90% capacity. Okay, so a lot more capacity required. It's going to take some new technologies, a lot of new thinking. We've been doing a lot of development on this already, so we're already kind of ahead of the game. We've got the best test lab in the industry. So
I was going to say, we can test our own stuff.
we can test all the way at minus 20 on a 100-ton unit. Nobody else has that capability. We've done a lot of this testing, and, we've learned things that we really didn't expect. We do lots of modeling before we go in and do a test. Okay, so we really think we understand things really well. But when we found when we get to these really cold temperatures, some of the things aren't working out as the models say.
Yeah.
So I think if some of our competitors out there that don't have the capability to test like we do, they could run into some trouble when they get into actual applications and see some things down there. So, another huge advantage we have over much of our competition is our 2-inch double wall foam cabinets. Okay, with the injected foam. When you start to get to these really cold temperatures, you're now, if you look at the delta T between the inside of the cabinet and the outside of the cabinet, gets to be very high. Okay, so that's a driver of, capacity is essentially the difference in temperature. Okay, so you start to lose a lot of capacity if you don't have a good cabinet at these really cold temperatures. So our cabinet is going to be a really nice advantage to have at these really cold temperatures.
Yeah, and there are many features that AAON has had historically that had made a difference, but now they're becoming crucial in order to truly be efficient. And so it's kind of like, instead of going from niche to mainstream, the mainstream is trying to become a little bit more like AAON.
It'll have to become more like us to meet the efficiency we have and the capacity and the life of the equipment that we have. It tends to lead the same directions that we came up with 20 years ago.
Correct.
Yeah. So what's this timeline on this challenge, though?
So the challenge, in general, there's a few deadlines. The main aspect of it is that you have to have products on the market ready for purchase in 2027. Okay, so we have to have, I forget maybe all the dates, but we have to have some prototypes available for field tests. I think that's maybe, do you remember, is that next year or?
Yeah, I believe it's next year.
Yeah,
so
2025.
So 2025, we provide a test unit to the DOE to verify our test results.
Right, yeah.
The end of this year, we provide our preliminary testing results to DOE for them to evaluate. And then we send a unit to them about mid-year next year. And then I believe it's in 2026 is when the field trials start.
Yeah, so, part of the challenge was, so we've got a group of manufacturers, okay? There's 6 or 7 manufacturers, if I remember right. And then there's also there's several different commercial customers who have signed up for this. And they're part of the challenge is that they've stated, we want these type products and we want them, we want our manufacturers to make them. So we're willing to do field trials of these products to help in the development cycle, and we want to work with these manufacturers to develop the products we need. Okay, so as we develop products, we'll do some testing, prototype lab testing with DOE, and then they'll go to these partners that they call them to take them and do field trials on our equipment. So all the manufacturers who've signed up for this challenge are going to be on these various customers' buildings. It's companies like Amazon and Walmart.
Oh, that's exciting.
And Kia, IKEA and places like that have decided, hey, we want these products. We want to test them. We want to be part of this process. So it's kind of a, it's our customers and the manufacturers working together to try to solve this problem.
That's phenomenal. I think there's just so much to learn about air source heat pumps. Things are going to continue moving. Who knows what the future exactly looks like? But it's not just the manufacturers. There are a lot of vendors that are working really hard in research and development to come up with the next compressor, the next controller, the next valve that allows us to get lower temperatures, higher capacity, bigger units.
Yeah, that's what's so great about competition, right? It makes us all better. So
absolutely.
Yeah.
Awesome. Again, thank you so much for your time. You guys are both always welcome. I know we're going to have you back soon.
And if you want to see what AAON means to him, watch episode 1 of AAON Inside.
Exactly. Awesome. To our audience, thank you so much for joining us again, for keeping up with Whitney here, my partner in crime. Don't stop, but just listen to this podcast. Go to our website. We have great content out there about Alpha Class and how it's making a huge impact in the industry. If you want to learn more about it, contact your local AAON rep. With that, this is the end of the episode. Thank you so much for joining us. Do not forget to like our episode and subscribe. Exactly.
Like and subscribe below.
Thank you so much. Whitney, say bye.
Bye.